Good morning, ladies and gentlemen of Precalculus. We are in our exercises here for chapter 1.2, quick review. So these all should be kind of a review, but so I can work some of these out, or I could call on people and or a mix of things. You want me to work out problem one? Sure. Now, there are different ways to do, there are a couple different ways to do problem one. One way I want you to increasingly look at it and see if anybody did it this way is, instead of adding 16, see if you can factor the left side here. And so if we leave the right side as this, and we find the factors of the left side, what are going to be what's the factoring of this x squared? Yeah, so Chloe said it here, x plus 4, x minus 4. And then what you have is, so what are your solutions going to be here? Yeah, so x equals 4, x equals negative 4. Sometimes you'll see it as x equals plus or minus 4. Another way, anybody do it by factoring like this? Okay. What I want you to do is I kind of brought this up. It was sort of a good thing. I want you, where you can, to see if you can do this by factoring. And part of it is me looking ahead to calculus and how that's helpful for calculus. Now, if you decided not to do it that way, did it still work out the same way? Yeah, it did, because what you had is you had x squared minus 16 equals 0, and if you add 16, you have x squared equals 16, and then if you take the square root of both sides, you have x is equal to plus or minus 4, right? So it ends up being the same thing either way you go.
So, can you go to the next one real quick?
Sure, happy to do that.
Like, trying to factor that one, how would you make it negative x squared? Like, would you just put negative x plus 3 and then x plus 3?
Let's look at that one. That's a very good question. Okay. Yeah, that's a very good question. To solve by factoring, the way I would do that is I'd go like this. That's the way I would do it. Does that make sense? Sure, she says unconvincingly. But you see, that's what it is, right? And now you've changed this into a more of a simple difference of squares thing. So then you'll have minus x plus 3. Right? And what happens is that just solving for this, it's like the negative almost doesn't matter, does it? Because it's like if you divide both sides of this equation by -1, right? Divide by -1, divide by -1. Well, that cancels out, and this still stays 0 here, right? And so we're still left with x equals plus or minus 3 as our answer, right? And then you can substitute back in to see if that is indeed the case, and it is, right? Do that, because you can replace this x with either plus 3 or negative 3 and still have that work out. Okay, now I think I'm going to call on somebody for number 3. How's that? And I'm interested in how you give me the answer. So I have everybody here on the wheel of names. Everybody knows that, right? It looks like we're going to get the Breister. Yeah, Bryce is the first person called on this year.
Feeling pretty confident.
All right, very good. I like that. I'm interested in the way Bryce has it, because they're just like problems 1 and 2. There are different ways to do these problems. So I'm interested in what Bryce has to say.
You know, I was looking at this, and I was just like, I'm just gonna go out on a limb here.
Okay.
You know, just ask Mr. G. So I just added 10.
Okay, let's go ahead and do that.
Yeah. To both sides.
The way Bryce is phrasing it, he's like keeping us in suspense. What is he going to do? So you have x is less than 10 is what you have.
And that's what I have.
So that's your answer?
Yeah.
That's your answer? Okay.
That's what I got.
Anybody else have something to add to that? Add or subtract or take away? Yeah, this is good. Thank you, Bryce.
Oh, yeah.
And this is an inequality notation. I do want to go ahead and I want to go ahead and make a pitch for what we call interval notation. If it's less than 10, we have in interval notation, we'd write as greater than negative infinity to less than 10. So we could write this in interval notation or inequality notation. But interval notation is eventually where we're going to be headed more and more. So that's why I bring that up. Okay?
What was another way to do that?
Pardon me?
You said there was more than one way to do that problem?
In this case, what I meant to say was there is more than one way to write the answer to the problem. Oh, very good, very good. And I want to, there's another way we did last year.
Yeah.
We did set notation too,
You
right?
had the same right.
Yes.
X such that X is less than 10. And you can even do a number line notation way of doing it. So that's what I meant. Thank you for bringing my attention back to that. All right, very good. Now that's what I call getting the year off to a good start, Bryce. That looks good.
Oh, yes.
Okay. So next we have number 4. Okay, I want to call on somebody for this one, 2, number 4. Yeah, I don't think for this class, we did a class video yesterday. I don't think I sent one out yesterday. I'm going to send one out today.
Yesterday wasn't much work. Yesterday was kind of just.
Okay, here we have,
Yeah. Or, hold on.
here we have the young lady that I described yesterday as being, what I say, cheerfully awesome. So will the cheerfully awesome person here do number 5, number 4 for us? Oh, sure, she says. And you are effervescently cheerfully awesome,
I
right?
think on the wheel last year I had a different name though.
Oh yeah, that's true. We may have to make that a feature again. Go ahead, Ed. We're kind of
I
distracted.
just subtracted 5.
Okay, subtracted 5. So you got negative x is less than or equal to negative 5. Is that right?
Yes.
And then?
And then I just took off the negative sign. Yeah, so I multiplied by negative.
So you multiply by negative 1. So you got x is less than or equal to 5. Is that right?
That's what I got, but don't you flip the sign or something?
Yeah, so that's right. We have to do that when we divide or multiply by a negative number, right? So we got to change the direction of our inequality. See, so I didn't even catch her. On the first day, I didn't catch her on it. So that's that, and then in interval notation, that will be like this, right? Okay? Thank you, Ed. 6, 5, excuse me. Okay, on this one here, do you want me to do this one?
Yes.
Yes,
This one
please.
here? Okay, find all values of x algebraically for which the algebraic expression is not defined, support your answer graphically. So we're going to be working on this a lot more in chapter 1.2. And what this is this comes to my, remember I showed that t-shirt yesterday, the inequalities, the types of discontinuities t-shirt. So what we have is our denominator, we can't divide by 0. So we said x minus 16. We know that cannot equal 0. So therefore x cannot equal 16. So this one here says for which is not defined, so the answer would be x equals 16 for which is not defined. That's going to be our answer, right? Okay. Since x cannot be 16, x equals 16 is the answer for which this expression is not defined. Okay? And it says support your answer graphically. What this is this gets back to if you graph this in our calculator, what you'll see here is you're going to see at x equals 16, you're going to see what at x equals 16? You're going to see, actually it's going to be at 1. So our horizontal asymptote, and I'll tell you why it is. Horizontal asymptote is going to be y equals 1. And so you're going to see your graphically is going to be like this. Does that look right? Did you graph that? Kendall, did you see that in your calculator? Yeah. What you have to do is you have to change your window. The standard window is not going to encapsulate that, right? So if you make your x max like 30 or something like that, you're going to see it like this. So Addie's looking at it, Gabby's looking at it. Is that what you see there, Addie? You don't see that? Let me do this again. Let me do it up here. I'll get the calculator right here. There we go. So we get x over x minus 16, right? And what you're going to see here is if you graph in a standard window like this, you're going to see this. But we got to change our window to be better looking. So to do that, go to our window. I'm going to go from like, I'll just make this to 30 and see what we get here. So that's what it looks like. So here's your vertical asymptote, and here's what that looks like. And your horizontal asymptote is at y equals 1. So what happened on this one here is when I did the little sketch, my scale was a little bit off because really the thing is going to look more like this, right? You see that? It ends up being the same thing, right? Okay.
You were right.
So that's the graph. So that's the graphical supporting of it. Yes.
What did you get y equals 1?
Okay, let me show you. Okay, because what happens is, and that has to do with what a horizontal asymptote is, and so you're asking kind of a leading question for where we're headed shortly in the class. What happens is that here you have x to the first power over x to the first power. So that means that as this expression, as you put in a bigger and bigger number for x, this thing simplifies to be 1. So if I let x equal 10 million or 1 million, so if x equals 1 million, what we're going to get is, I'm going to get 1 million, oops. I'm going to get 1 million. This is for x equals a million, right? Over x equals 999,984. What is this number very close to? 1, okay? And the same thing. So as we approach infinity, this thing goes to 1. As we approach negative infinity, this thing also goes to 1. And so that's why our horizontal asymptote is 1. And we're going to get into the techniques. We're going to talk about Betsy Bobo Botu. You ever heard about Betsy Bobo Botu? We'll talk about this year, and we'll talk about that in calculus next year too. But that's how I know, okay? That was a very good question. That was an excellent question. I'm going to give you credit for just that question. Okay, I want you to go ahead and do this one. You want me to do this one too? Or do I choose somebody to do? This one here has a little more complexity to it. That's what I'm saying. And I want to get through this pretty fast today. We'll go to...
Yeah, you can do it like this.
Is this still?
I know that's how it looks like. How do you know what this one looks like?
Okay, this one here, we have, for which is not defined, we have x squared minus 16 cannot equal 0. So therefore we have x plus 4, x minus 4. So x cannot equal plus or minus 4, which means our answer is going to be x equals plus or minus 4. Does that make sense? So that's where the function is not defined, because if either one of those is true. Now, in this case, our horizontal asymptote is going to be 0. And to do this without a calculator, you have to do sign chart analysis, which we haven't done in this class yet. We're going to get to it, I hope, later this semester. But so basically, not knowing how to do that much yet, you could just put in x over x squared minus 16. So x squared minus 16. And so you have this thing right here. I'll go to zoom 6. So this will be a graphical representation of that. You can see the horizontal asymptotes. I mean the vertical asymptotes where x equals -4 and x equals +4, right? So there's your graphical support. And here's your answer. That's number 6. This one right here, different type problem. Now here, what's going to be our restriction of this one right here? What do we know about x minus 16? What can you not take the square root of? A negative number, right? So therefore we know that x minus 16 has to be greater than or equal to 0, right? And so therefore x has to be greater than or equal to 16. And it says support your answer graphically, and to do that, if you graph this in your calculator, what are you going to see? Well, I will show you what you're going to see. You're going to see the function value will start at 16. So if you go over to 16, it'll start right here, and then it'll go like a square root function like this. Anybody graph that in the calculator? Well, if you did, that's what you would see. Okay? So that's going to be our, and then it says for which the expression is not defined. So we say not defined for what? For x is less than 16, right? If you put this in a calculator, you're going to see errors all the way for less than 16. Okay? So this will be our answer. This is the graphical support of that answer, and that's number 7. And this one right here, for not defined, we know that this here has to be what? Greater than or equal to 0. So x squared plus 1 has to be greater than or equal to 0. Well, that's always going to be the case. And here you have in the denominator x squared minus 1 cannot equal 0. And so that's going to be x plus 1, x minus 1 cannot equal 0. So x cannot equal plus or minus 1. So therefore, where the function is not defined, that would be x equals plus or minus 1. So that's where it's not defined. And then for corroboration in our calculator, graphical corroboration, we go here and we put in square root of x squared plus 1. And then down here we have x squared minus 1. Delete, delete, there we go. So we should see it right here. And you can see that graphically, right? Not defined at x equals -1 or x equals +1. And we're going to do it later on, like I told you, sign chart analysis in the semester where you're going to be able to do this without a calculator. It's just getting the experience at it. And then this one right here. Okay, x, for a numerator, x plus 2 has to be greater than or equal to 0, right? And then down here, we're going to have 3 minus x has to be greater than 0, right? Because we can't divide by, this can't be negative number, but it can't even be 0. So if you just solve for this, we have x has to be greater than or equal to -2. And now we're getting to what Addie was showing earlier, right? We subtract 3, so we get negative x is greater than -3, but that's going to be x is less than 3, right? So x has to be less than 3, but greater than or equal to -2. So, so basically, on a graphical support, a number line, we know x has to be greater than or equal to -2. So here's greater than or equal to -2. Oh, should be -2, right? -2, like that. and also x is less than 3. So here's less than 3. So we have all this right here. And then it says, where is this not defined? Well, here's the graphical support. So where is x not defined? So x is not defined for x is less than -2 and x is greater than or equal to 3. So that's where the function is not defined. So it's defined here, but not defined everywhere else.
Mr. G, how did you know that the denominator had to be greater than 0?
Okay, the reason is, see up here, I knew this had to be greater than or equal to 0,
Now,
but why does this have to be greater than 0 here?
well, it can't, because the denominator can't be 0, right?
Yeah, because you can't divide by 0,
Yeah.
so that's why. So that's why they're different. Okay? See, that was a good question. I'll give you credit for a good question too. Okay? Okay, good job. And then, and we're going to be coming back to this in the next one right here. Okay, on this one here, the only thing you have is this one here. I would just tell you x cannot be equal to plus or minus 2. Okay, and I want to get on with the next thing here. And what that is we're going to 31. Okay, so we got 15 minutes of class left.
16, Mr. G.
What I'll do is what I want you to do is I want you to be taking some notes here. And so I want you to get out your notebooks for this.
Are we trying to say, Mr. G?
Yeah, you'll turn it in. Bryce will get it for us, won't you, Bryce? Thank you, Bryce.
Yes, I sure will.
Gene, you don't have a trash can by the door anymore.
I don't have a what?
A trash can over there.
Yeah, they
Said that.
don't.
I just noticed the end of it.
Yeah.